Okay, welcome to lecture 8.7. Is that right? Yeah, 8.7. Okay. Um, More on McKelvey-Palfrey. Let me give some of the technical details. Okay, so this is there's section 1 or section 2, the first technical section. What they do first, let's do some definitions. Oh, and here, one thing I want to do, I think this is a good idea for lots of papers in general. If it's a very technical paper, sometimes hard to follow, lots of math and especially lots of definitions. Just get a pad of paper, and to the side, every time the paper writes a definition or something, have in mind a simple example to which the paper can apply. And so that's what I'm going to do. I'm going to write McKelvey-Palfrey's definitions, but then I'm going to say, well, what if we were applying this to the ox game? So remember ox game? It's like matching pennies. There's two players. Each player has two actions. A has A1 or A2. B has B1 or B2. Okay. Um, Now, all right. So here, this is the general case on the left side. So players and Palfrey, right? Big N, and it equals 1 dot to N. Now, in the Ox game, the players are just two. Wait, I was going to say players 1 and 2. Yeah, okay. They're actually player A and B. Um, you know what I think I'm going to. I think I'm going to use A and B. Even though technically McKelvey-Palfrey called them numbers. Okay, now, next there's pure strategies. And, okay, so this is a pure strategy for player I. You can play SI, and that is an action. Okay, so I think this is. Yeah, I think. Man, my notes are not good. I can't. That may be a bold SI or a capital SI, and so that is the space. Those are the possible pure strategies that I can play. So player I can play, and this equals okay S I 1 dot 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 to S I capital J. Okay, so there's capital J possible. Okay, so McKelvey-Palfrey called them pure strategies. Commonly in game theory, we call them actions. So um, a strategy is either play one of the possible actions or do a combination, somehow mix over two or more possible actions. So if you play a pure strategy, you're just picking one action. So we could call these the possible actions to player I. And then so as subscript A, actions of player A would be A1, A2. Actions of player B equals B1, B2. Okay. Okay, next. Um, McKelvey-Palfrey define okay, P sub I of S I J. Okay, that equals probability player I chooses action Sij. Okay. All right. So now, okay, in the Ox game we didn't describe that, but let's say it. Um, PA1 and PA2. So that's for player one, but we can get rid of PA2. That's just 1 minus PA1. There's only two possible actions, so the second one's got to be 1 minus the other one, the first one, and then player B can play B1 or 1 minus, or B2, which is 1 minus PB1. Okay. Okay. And delta I equals space of mixed strategies. Okay. Now, for player A, the space, all we need to know, if we know PA1, we know PA2 because it's just 1 minus PA1. So really, the space of strategies for player A is just 0, 1. So it's any PA1 in 0, 1. Okay. Turns out if he had 3 actions that he could have done, then there would be PA1, PA2, and then the third one, PA3, would just be 1 minus those other two. But then this sigma A would just be 0, 1 squared. So it could be all the possible. So PA1 could be anything in 0, 1. PA2 could be anything in 0, 1. So you'd need two vectors to describe the space of the actions. Okay. So sigma A, and then sigma B is similarly 0, 1. Okay. All right, now, UA. All right. All right. U bar. Okay. Darn it. U bar for a player and an action. So U bar for, say, player A, player A1. This is what we're going to call the scene utility. Okay. Um, so here's where we're going. Let me explain. What we're going to do is McKelvey Palfrey are going to look at some of these experimental games. What I'm going to call the scene utility, that's the actual money payoff that the researcher is giving in these experiments. Okay. What we're going to do, what McKelvey Palfrey are going to do, is say maybe there's an unseen utility too, that somehow you get some sort of psychic utility from playing A1 or extra utility for playing A2. Okay. So it's going to be the error term that we're going to add on to this. But for now, the scene utility is the money payoffs that are involved in these experiments. Now, you could generalize this to other things. It doesn't have to be an experiment. So, and I think McKelvey Palfrey try to keep it general. That comes at the expense of not making it concrete, and so you don't know what does that mean. What does U bar really mean? So, so U bar, and by the way, so this is going to be U bar AA1 of P. Okay, P is the probability. It's the vector of probabilities that all the players are playing various actions. Okay, now it's going to be even more difficult than that, because what we're going to do later is we're going to take this P and then we're going to compute a different probability. Okay, and it's not clear which is which. Okay. Um, Here is where we're going. This P, think of it like a seed value. These are like we're doing an estimation technique. You plug in seed values. From the seed value, then you do an iteration, and then you see, is my estimate, how does it differ from the seed values? If it differs too much, we got to do another iteration. We got to keep on doing iterations. We're going to do something like that here. So we're going to specify a seed value of the probability that players are going to do different actions. And then from those seed probabilities, we're going to see what their optimal actions are, their optimal probabilities are from those seed probabilities, and see if they differ. If they don't differ, we know we've found the right ones, in a sense. They're all the equilibrium probabilities. But if they're different, then either have to try a new seed probability. Anyway, getting ahead of myself. But for the moment, think of that P as a seed probability. Here is another way of thinking about it. Okay, in game theory, I like to use, when I teach game theory, especially my undergrad class, I like to think, I use a concept that one of my old professors when I was in grad school, Dave Barron, used to do. He would say there's an equilibrium God. And the way you check if something is a Nash equilibrium, Dave Barron says, think of it this way: the equilibrium God specifies strategies for all the players, announces strategies for all those players. And then what happens, each player says, well, let's assume that all the other players will do what the equilibrium God says. But now let's see if my optimal action is really what the equilibrium God said, given everyone else is following the equilibrium God. Okay. Something like that is going to be involved with this P. It's like the equilibrium God says, here are the probabilities that you play these various, do these various actions. Okay. So P is going to be, in this case, it's going to be a vector. So for the Ox game, it's going to be PA1, PB1. So if we know the probability, so the equilibrium God announces a probability, player A plays A1, announces probability, player B plays B1. Once we're given that, we know PA2, that's just 1 minus that, and we know PB2, 1 minus that. Okay. All right. Now, for the Ox game, this U bar A1P is just defined to be, it's the expected payoff, the expected utility if A plays A1 and B mixes according to PB1. Okay. So now, if A plays A1, A's payoff is 4 times the probability B plays B1 plus 0 times the probability B plays B2. Okay, so this is going to equal 4 times P B1 plus 0 times 1 minus P B1. So I didn't need to write that 0. Just equals this, 4. Okay. Now, uh, let's write U A2. U bar A A2 of P. That equals, all right, so this is defined to be A's expected scene utility if she plays A2. Okay, so if she plays A2, she gets 0 if B plays B1, 1 if B plays B2. Okay, so this is going to be 0 times P B1 plus 1 times 1 minus P B1. Okay, equals 1 minus P B1. Okay, so here we have U bar A2. All right, now U hat A1 just equals U bar A1 plus epsilon A A1. Okay. So what we say is player A gets the scene utility, okay, which is this in case this here is going to be 4PB1. Actually, let's write that 4PB1 plus epsilon A A1. Okay, plus there's this random component. So it's like the McFadden travel case from doing this action. Okay, now here's the ad hoc assumption that I talked about earlier. In economics or in game theory, usually we say that your payoffs are not over the action that you take. The payoffs are over the outcome. Okay, so if you want to be a stickler, if we're going to do this according to the conventions of game theory, we should have an error term one error term if this is the outcome, another term if that is the outcome. But Kelvin Palfrey don't do that. They only have one error term. They say there's some unseen utility from playing action 1. Okay, there is not unseen utility from getting that outcome, or unseen utility from getting that outcome. This is the ad hoc assumption. They get the player. We assume that player A gets these unseen utility according to the action that she does. And this is basically how they get around that Bresnahan and Rees problem. Bresnahan and Rees added an error term for every different outcome, and their paper was a mess. Okay, Kelvin Palfrey said, "Look, we're just going to have one error term, or two instead of 4 error terms. We're going to have 2. One, there's some unseen utility from playing action A1, some unseen utility from playing action A2. Okay, all right. So that is a little ad hoc. I give them a break. I say that's fine. Okay, so now we have U bar A1. Okay, so notice it doesn't depend on the outcome, this error term. It only depends on the action. Okay, and then we're going to have U bar A2, and that just equals 1 minus PB1. So it's a U bar A2 plus epsilon AA1. Okay, so now plus epsilon A comma A2. Okay, all right. Now, all right, so far we're just focusing on player A. Okay. All right, now sigma A1. Okay, it's a function of u. You know what? I'm not gonna write that. This is sigma AA1. It's a function of some stuff. Okay, that's all I'll say for now. That is defined to be the probability that A plays A1, chooses action A1. All right, so this happens to be the probability that U hat A1 is greater than U hat A2. Okay. um, okay. Now we can do this similar thing. So now let's treat those payoffs as given, okay? I'm going to say this is a function of some stuff. It's a function of the payoffs, it's a function of the distribution of the error terms, a function of a lot of stuff. But for the moment, let's just focus on one parameter, and that's the p's, the PA, A1, PB, B2, and just call that vector. That vector just equals P. Okay, so actually I'll just write out PA A1 PB B2 rather than write P. So what we have is sigma A1 is a function of PA A1 and PB B1. Okay, and that equals the probability A plays A1. And now you should have said, well, wait, I thought PAA1 is the probability A plays A1. Okay, good point. What's going on here is this PAA1, that's the probability that the equilibrium God announces. That's the seed, or if you like, the seed probability. Okay, so sigma AA1, think of this as the actual probability given the seed probability. Okay, so player A looks at PAA1, PBB1, what the equilibrium God says, and then says, all right, what's the probability that my utility is going to be from action A1 is going to be greater than action A2. All right, so that's a little fast and loose with that. Actually, what's going to happen is player A actually knows his epsilon term. Okay, so it's like the McFadden model. It's like the random utility model where each person knows his own error term, but the researcher does not. So let's think of it this way. Suppose we, the researcher, hear what the equilibrium God said, PA, PB, B1, and then we compute sigma AA1 given those error terms, given the distribution of those error terms. And that sigma might be different from what the equilibrium God said. Okay, so what we're looking for, eventually, we want an equilibrium where the sigma is equal to P. Okay, so so the sigma equals, remember this, so this is probability A plays A1 given the equilibrium God announced these values, PA, A1, P, B, B1. Okay, that's what that is. All right, now what we want is an equilibrium. So this is what Halford Keller called the quantal response equilibrium. And this is what we want is a set of PA A1 PB B1 such that sigma A1 of PA A1 comma PB B1 equals what the equilibrium God said for PA A1. And then the same thing is true for player B, sigma B B1. So given A1 P B B1 equals what the equilibrium God said, PB PB1. Okay. So remember, these sigmas are what we calculate. We, the researchers, say this is the actual probability that A will play A1, sigma B, that's the actual probability that B will play B1, and it's a function of the seed probabilities that the equilibrium God said. It's an equilibrium if the sigmas equal the p's. Okay, that's what we're looking for. All right. Okay, now, here's what McKelvey Palfrey do. Okay, so in their first section, so they have a lot of notation. Look at all this, a lot of complicated notation. And what they do is theorem one is they show that for any epsilon, some very, I can't even remember the conditions. For these very weak assumptions about the distribution of epsilon, I think it has to have, I can't remember. I was going to say it had to have infinite tails, but I'm not even sure if that's true. I think it might be continuous. I don't even remember what the technical conditions were. So given some technical conditions about epsilon, so they don't assume a particular distribution. They aren't saying it's normal or Weibull or logistic or anything like that. It's just some distribution, and it satisfies these weak technical conditions. Given that, theorem one says there exist PA, PB, so these P's that the equilibrium God said that will make this equation true. Okay, so there will exist an equilibrium. Okay, as long as those epsilons have those weak technical conditions. Okay. Now, here's a story. When John Nash wrote his great theorem, and this is, I hope all of you at some point watch A Beautiful Mind. Great movie. Supposedly when Nash did this, I think he was a grad student even when he did this, and he showed John von Neumann his paper, and von Neumann kind of dismissed it, said, "Oh, all this is a fixed point theorem." Okay, that's what McKelvey Palfrey do. You'll notice the proof of their theorem one, I think it's Brouwer's fixed point theorem. It says there's like two sentences, and then it says by Brouwer's fixed point theorem, there exists a set of P's such that those sigmas equal the P. And that's it. It's like a two-line proof. And I'm sure if von Neumann had seen McKelvey Palfrey's section one, their theorem one, they said, all this is a fixed point theorem. There's nothing impressive about this. Brouwer did all the work for you. I'm sympathetic with that. It's not that interesting. And there is a ton of notation just to show that. Okay. So keep that in mind, that section one, really all you need to do is skim it. Okay. The key is Palfrey, do this kind of mental gymnastics just to show an equilibrium exists. Okay. But that's what we're looking for. Eventually, we're going to have homework where you're going to actually have to guess seed values that give you the right sigma. So you're going to have to keep on guessing P's until you get the right sigma. Okay. But Kelvin-Palfrey theorem one says there's got to be at least one set that works. Okay. So that'll be useful for your homework. Um, okay, let me tell you what's going on here. Um, so we're going to have these epsilons, epsilon A, A1, epsilon A, A2, and we're going to use those to say what is the probability A plays A1. This probability U hat is greater than U hat A, A2. All right. Given that, okay, suppose we want to have a convenient way to express these probabilities, say in a closed form version. What's a good assumption to make of these epsilons that's going to give us a nice, clean, elegant form for these probabilities? Hit pause. Okay, if you're back, hopefully you got the answer right. The answer is Weibull. Okay, or extreme value 1. That's what we're going to assume, is that these error terms are distributed Weibull. From that, we're going to get those nice probability terms. And that is what McKelvey and Palfrey do in the remaining section of the paper. And they actually get some really interesting results, but they do it at the expense of having to make a very particular assumption about the error terms. Okay, so that is the basis, okay, of what McKelvey Palfrey do. So hopefully you've got enough that I think you're capable of reading it, understanding a big chunk of what's going on in that paper. Okay, so given this, I think you're ready to read the McKelvey Palfrey paper. Once you do that, then we'll finish up the remainder of this lecture, and that'll be in session 9. Okay, see you then.